Assalamu alaikum. Physical Geology. Chapter 10 Ocean Basins, Origin and Evolution of the Seafloor, presented by Khalil Amrouni, PhD in Geology, Texas A&M. Khalil Amrouni is a staff member at the Department of Earth Sciences, Gar University, Benghazi, Barga State, or Cyrenaica State. The used reference for this talk is Essentials of Geology. This is the Department of Earth Sciences at Gar University, the main entrance here of Gar University. This is Idris Sanusi, the Prince of Barga State and the founder of Gar University. And here's the flag of Cyrenaica State behind the Prince Idris. This is Benghazi city, capital of Cyrenaica State. Omar al-Mukhtar, the chief commander of Sanusi army. And this is a map of Barga State or Cyrenaica State. Outlines the ocean floor, measuring ocean depths. They used weighted lines, eco-sounds, and satellite radar altimeter. Types of seafloor sediments: lithogenous, those driven from rocks; biogenous, driven from organisms; and hydrogenous, driven from water. Seafloor sediments and climate: three major units of ocean basins: continental margin, the ocean basin floor, and the mid-ocean ridges. Continental margins, they have three subdivisions: continental shelf, slope, and rise. The ocean basin floor, they have trenches, abyssal plains, and volcanic peaks. And then we'll go to coral reefs and atolls and how they form, and then oceans opening and closing, which is basically Wilson cycle. The ocean floor. So Earth, we know Earth is dominated by oceans, and the area of the Earth about 510 million square kilometers. 61% of that area is covered by water, and 39% is land. And the southern hemisphere is almost 81% water, while the northern hemisphere is called land hemisphere. The Earth beneath the sea. So when they try to measure the depth of the water to reach the surface of the ocean, they tried many methods. The first one was weighted lines, just dropping ropes with weight until they touch the surface and measure the length of that rope. And then after that, they used technology, eco sounds, sound waves basically. They transmit them to the bottom until they touch the bottom and then reflect back to the surface. And there are receivers, we call them hydrophones, to receive these reflected sound waves. And by measuring the time that the waves traveled from the ship down to the bottom and then from the bottom back to the receivers, they managed to calculate the water depth. All what they did, the velocity of the wave sounds in water, which is 1,500 meters per second, multiplied by half of the travel time, because we know the waves travel to the bottom and then reflected back to the hydrophones. So we need half of that travel time. And this is the way how they were able to measure the water depth. So the topography or shape of the ocean floor is called bathymetry. And the modern bathymetric techniques, we said sonar, side scan sonar, and high resolution multi-beam, all these sound waves. And then they were able also to measure or map the ocean floor from space, use its satellite radar altimeter. So these wave methods, eco sound, sending waves to the bottom, and then waves red, to the blue one, and then reflected back as red waves. Just representation or presentation for the waves, reflected signals, and then these signals will be detected by the hydrophones, and this way the bottom depth of the ocean floor or the bottom of the ocean can be mapped. This is another way: side scan and multi-beam sonar. This is the multi-beam sonar, and this is the side scan sonar. So still using waves to map the bottom of the surface of the floor of the ocean floor. And here's satellite altimeter. Using sending signals, radar altimeter, to the ocean water surface, and then the waves will be reflected back, the pulses, from the sea surface and detected by the radar, the satellite here. Theoretically, the ocean surface should be flat, but due to the changes in the topography, like there are valleys and mountains, and these mountains under the sea, they have gravitational effect, and that cause the gravitational attraction, and that gravitational attraction causes the changes in the topography or anomalies at the surface of the water. And the satellite altimeter just detecting these changes that depict the bottom of the ocean, or bathymetry. Seafloor sediments, seafloors, which is deep ocean floor, shelf slopes, mostly dominated with mud-sized sediments. But still, we have sands. As you go from the ocean, from the beaches along the shore to the deepest parts of the ocean, the grain size changes from sandy to muddy size. So grain size decreases as you go to the ocean in general. Now, types of seafloor sediments. We have three types based on their origin. Lithogenous sediments that derived from rocks, biogenous sediments that derived from organisms, hydrogenous sediments that derived from the water. Okay, seafloor sediments and climate. Let's go to the seafloor sediments. Lithogenous grains which were weathered from continental rocks and transported to the ocean. So the sand-sized particles settle near the shore. The smallest particles may be carried by ocean currents to settle to the ocean floor. So will settle farther deeper, the finer grains. Biogenic sediments consist of shells and skeletons. This debris is produced mostly by microscopic organisms living in the sunlight water near the ocean surface. So near the ocean surface, the water itself, the ocean water, there's microscopic organisms, and their shells or skeletons made up of calcareous material or siliceous material. And the calcareous, we call them calcareous oozes or siliceous oozes. And they find out the calcareous oozes can be found after they die. Because they live close to the surface, after they die, they drop down or rain down to the surface because they live in huge amounts or huge quantities of these calcareous oozes and siliceous. The calcareous oozes can be found up to the depth of 4,500 meters. Below that, the calcareous or calcium carbonate will be dissolved. And then you'll find siliceous oozes under the depth of 4,500 meters. And examples of siliceous oozes or biogenous siliceous, opaline skeletons and radiolarians. And hydrogenous sediments consist of minerals that crystallize directly from seawater throughout various chemical reactions. And one of them, manganese nodules. So, what's the relation between seafloor and climate changes? They find out the number and type of organisms living near the sea surface change as the climate changes. And we know when these organisms die, their shells settle down to the seafloor and then lithified and became these skeletons, became part of the sedimentary record. So if we have sedimentary record, if we have these organisms in the sedimentary record, by studying, their numbers and the types of the organisms, we can tell about the climate changes. Three major units of the ocean. So oceanographers divided the ocean topography or bathymetry into three units: continental margins, the ocean floor, and the mid-ocean ridges. Here we'll have a map between uh, North America and Africa. So if we take a section from A to B through the mid-oceanic, this is the Atlantic Ocean. What we'll see from A to B. Mid-oceanic ridges here in the middle. This is the cross-section, A to B. So from North America, we have continental margin, deep ocean ridges, and then mid-oceanic ridges. Those are the three units that we have. The same three units will be repeated here. Continental margin from the African side from B. Deep ocean ridge, deep ocean basin, and mid-ocean ridges. So what do we have in the continental margin? One, continental shelf. Two, slope, very steep here, kind of slow. Three, continental rise. And then deep ocean basins will have seamount and abyssal plain. And then mid-ocean ridges will have rift valleys, number six. The same thing will be repeated if you come from the African side. You will have continental shelf, continental slope, and then continental rise. And then you'll have seamounts and abyssal plain, and then rifts, or rift valley. This is the rift valley here. Okay? This is diversion zone, opening. In this example, we don't have conversion to all diversion. And this example we call passive margin. So continental margin, this is the first. We'll start with the continental margin. We'll see the three subdivisions in it, and then we'll go to the deep ocean and then mid-ocean ridges. Continental margin includes the continental shelf, continental slope, and continental rise. So what's the continental shelf? Is a gently sloping, submerged surface extending from shoreline toward the deep ocean basin. The continental shelf is about 80 kilometers wide and 130 meters deep at the seaward edge. The continental shelf represents almost 7.5% of the total ocean area. And it's economically very important because they're sites of mineral deposits and petroleum and natural gas too. The continental slope, now the first part continental shelf, now continental slope, mark the seaward edge of the continental shelf. It has a steep gradient compared to the continental shelf. The continental slope has steep gradient. Also here, the continental slope marks the boundary between the continental crust and the oceanic crust. The third one, the continental rise. In regions where trenches do not exist. So if we do not have trenches That means we're passive marshes. The steep continental slope merges into more gradual incline known as continental rise. The continental rise, the gradient here is between 4 to 8 meters per kilometer. And the continental rise may extend over hundreds of kilometers. Note the deep, steep side valley known as submarine canyons originate on the continental slope. So let's see the picture here. So here we have continental shelf. This is the continental margin. We have shelf, and then we have steep slope, and then we have rise. Okay, so canyons, submarine canyons, they originate here at the continental slope mostly. Okay, but the sediments moved from the shelf through the slope, through the rise, and they deposit on the basin and create turbidite sediments. And they go through turbidity currents down. So this is basically passive continental motion. It has three parts: shelf, slope, rise. Shelf, gentle, and the slope abrupt, gradient, and the rise is very gentle, 4 to 8 kilometers. The gradient 4 to 8 kilometers per minute, 4 to 8 degrees per kilometer. Okay, let's go back to the second part. So this continental margin. Now the features of the continental rise surface. Interrupted by submarine canyons, correct, or by submarine volcanoes. This is for the continental rise. Can be interrupted by submarine canyons and submarine volcanoes, not completely buried by sediments. Okay. So we have examples like Congo Submarine Canyon off the west coast of Africa. And canyons are believed to have been excavated on the continental slopes. Canyons may reach 3 kilometers in depth. Canyons have been excavated by turbidity currents, yes. So what about turbidity currents? Turbidity currents are very important sediments. Turbidity currents, so when sediments or laden sediments move it down the slope, these dense sediments, sediments mixed with water, when they move it down the slope, they create turbidity sediments. So they are created when sand and mud on the continental shelf and slope are dislodged. Here's some important notes. Turbidity currents usually originate along a continental slope and continue across the continental rise and come to rest along the ocean basin floor. So they travel long distance. And there's a very important feature in the turbidity currents. We call it the graded bedding, which changes the grain size of the sediments from coarse to fine as you go upward in the beds. Okay. Now the second part, the ocean basin floor. So we're done with the continental margin with the three parts: shelf, slope, rise. Now we'll go to the second part, the ocean basin floor. What it has: trenches, abyssal plains, volcanic peaks. Features of the ocean floor basin. The ocean basin floor lies between the continental margin, as we said, and the oceanic ridge system. And the size of this area is about 30% of the Earth's surface. So what's the deep ocean trenches? The sites where moving crustal plates are destroyed. So trenches mainly their subduction zones. What they have, always when we have subduction zones, we have earthquakes and we have volcanic activities. And trenches in the open ocean are paralleled by volcanic island arcs. Yes, because we have volcanoes that create volcanic arcs. Trenches, they form just when you have subduction zones. Abyssal plains, different. They are very flat features. These regions are the most level places on Earth, so they're very flat. They are found as part of the seafloor in all the oceans. Now sea volcanic peaks, deep-sided, and they are called seamounts. Seamounts are isolated volcanic peaks. They rise near the oceanic ridges, where the plates of the lithosphere move apart. Divergent plate boundaries. So seamounts, they form in divergent plate boundaries. Okay? But trenches form in convergent plate boundaries. Now guyots are submerged, flat-topped seamounts. It's a special type of seamounts. We call guyots. Also guyots possibly hot spots formed away from the ridge crest. Volcanic hotspot. Okay? So if we want to see trenches, these trenches when you have continental and oceanic, the oceanic just dives below or under the continental due to the difference in the buoyancy force. Continental crust is lighter, oceanic crust is heavier, so it just subduct down under and it creates a groove, deep groove, we call it trench. And always there's igneous activity here due to the melting of the oceanic crust under the continental crust and creates continental volcanic arcs in the continent. If there's islands, if they were, it was like these both plates, if they were like both oceanic, will create island arcs, oceanic island arcs. So this place, it's called Mariana Trench. It's a groove, deep groove, and it's subduction zone. Now the third part, mid-ocean ridges or mid-oceanic ridges. So they stand above the adjacent deep ocean basins, and we'll say why they're higher in elevation, stand above. Ocean ridges consist of layers upon layers of basaltic rocks that have been faulted and uplifted. So mid-oceanic ridges made of uplifted, faulted layers of basaltic rocks. They are not sedimentary, basaltic rocks. So these ridges, mid-oceanic ridges, marked by deep rifts, like deep valleys or rifts. And these rifts are flanked by ridges and lines of peaks and extended outwards. So they are flanked by ridges and lines of peaks of mountains, small seamounts, and extended outwards. What's the axis of these ridges? The center of these ridges. The axis of the ridges are marked by frequent earthquakes and by much higher heat flow through the crust. Why? Because the rifts at the center of the ridges are sites where new magma wells up from the asthenosphere below, continually creating a new oceanic crust. So the center of the rift is the place where we have, the divergent boundaries. This is where new magma coming from the bottom and upwells and pushes both plates away from each other and creating a new oceanic lithosphere. So here they're saying, oh, drifts therefore represent divergent plate boundaries where seafloor spreading is taking place. Correct. The primary reason for the elevated position of the ridge system is the fact, so why they are standing above, that newly created oceanic crust is hot. So if you have hot magma coming up, and therefore occupies more volume than cooler rocks of the deep ocean basins, because when it's hot, low density and higher volume. But when it cools down, it gets denser and will sink down. But the hot ones will stand up. Distribution of oceanic ridges, these red lines here, this is the Atlantic mid-oceanic ridges. And you can follow them along the Indian ridges, East Pacific. Close-up view of the ocean floor. And we have here coral reefs and atolls. What's coral reefs? Coral reefs are calcareous, calcite-rich, of skeletal remains, excretion of corals, and certain algae. They are coral and algae. And they are confined largely to warm waters. Always you need warm waters to have these coral reefs. We have a special form of coral reefs we call atolls. So atolls is just coral reef surrounding a huge lagoon. How these coral reefs formed? Coral reefs formed on the flanks of sinking volcanic islands. Oh, that's weird. So we have volcanoes, volcanic islands, fringing coral reefs formed around them, and we know these volcanoes or volcanic rocks, they were hot, and that's why they're standing above the ocean. But when they cool, it will start sinking down. But the corals, the fringing corals, will keep growing up close to the water surface because they need light. And that's how the lagoon starts forming between the sinking mountain or volcanic mountain and the fringing to create barrier reefs. So fringing, that means touching the island, but barrier, there is a lagoon between the mountain, that sinking mountain, and the coral. As the mountain keeps sinking, the lagoon, the coral reefs, or the atoll, as we call atoll, will keep growing up and surrounding the lagoon. This is how it forms, basically. And the mountain just sinks below the water surface of the ocean. So ocean ridges and seafloor spreading. We know ocean ridges, oceanic ridges are places of seafloor spreading. Seafloor spreading occurs along relatively narrow zones called drift zones, correct, located at the crest of the ocean ridges. So rift zones are the places where the seafloor spreading occurs. And as plates move apart, magma wells up because we push plates away from each other at the divergent boundaries, and a new magma comes up into the newly created fracture and generates new slivers of oceanic lithosphere. New lithosphere moves from the ridge crest in a conveyor belt fashion. So as a new lithosphere created, a new magma will come up and push this new oceanic crust or lithosphere away, both sides. Zones of active rifting are 20 to 30 kilometers wide. And here just the same question, why oceanic ridge is elevated. Primary reason is because newly created oceanic lithosphere is hot and occupies more volume than cooler rocks. As the basaltic, this is the first reason why it's high. And then what happens after that? As the basaltic crust travels away, pushed away from the ridge crest, it's cooled by seawater. And then what happens? As the seawater moves away, it thermally contracts and becomes more dense. So as the lithosphere moves away. So lithosphere at the crest, it's hot and occupies more volume. That's why it's standing up and it's high in elevation. As it travels away or pushed away from the crest and cooled down by the seawater, it becomes denser and heavier and sinks down. So ocean ridges and seafloor spreading. Here they said ridge system exhibit different topographic differences. So why we have different, or why the oceanic ridges are topographically different. They are different due to the spreading rate. So let's look at the slow, intermediate, and high. Let's look at the slow spreading rate. If you have low spreading rate, you'll have a rift, deep rift, rift valley. And the magma chamber is poorly developed. So you have rift, down, valley. But if the spreading is fast, you will have a swell. And the chamber here, magma chamber, is very well developed. So it's bulging up when you have fast spreading. Okay, so let's go back. See, at slow spreading rates, 1 centimeter per year, a prominent rift valley, so we'll have rift valley develops along the ridge crest. It's usually 30 to 50 kilometers across, wide, and 1,500 to 3,000, like 3 kilometers deep. If you have intermediate spreading rate, 5 to 9 centimeters, rift valley, valleys that develop are shallow and less than 200 meters deep. But if you have very fast spreading rate at the mid-oceanic ridges, more than 9 centimeters per year, no median rift valley develops. And that area, you'll have like a bulge instead. And that area usually narrow and extensively faulted. So that's why we have different topographies at the mid-oceanic ridges, the spreading rate, main control. Nature of oceanic crust. So here we study something we call Ophiolite Complex. They find out 4 distinct layers in a sequence of rocks called an ophiolite. So we have layer 1, sequence of unconsolidated sediments, that's at the very top. Layer 2 consists of pillow lavas. Layer 3, interconnected dikes called sheet dikes. And layer 4, we call it gabbro. So let's look at the figure. So here we have this deep sea sediments, basaltic pillow lava, and then these dikes or sheeted dike complex, layer 3. Layer 4 is the gabbro, which is layered gabbro, and then mantle peridotite. So This is mantle crust, the mantle peritite, but this one is oceanic crust. Start from layered gabbro complex, sheeted dikes, and basaltic lava, and then deep sea sediments. This is, as a whole, we call it Ophiolite Complex. How it formed? Let's go back here. So formation of oceanic crust. Basaltic magma originates from partially melted mantle peridotite from the bottom. Molten rock injected into fractures. The fractures above the magma chamber creates the sheeted dike complex. So the magma from the mantle here created gabbro and then started injected into the fractures, created those sheeted dikes. What happened again? Next, the submarine lava flows, chill quickly, and congealed margin is forced forward to produce large tube-shaped protuberance known as pillow lavas or pillow basalts. And then interaction between sea, water, and oceanic crust. We have here the black smokers. So seawater circulates down through the highly fractured crust. Basaltic rocks is altered by hydrothermal metamorphism. And then hydrothermal fluids dissolve ions of various metals and precipitate them on the seafloor as particle-filled clouds called the black smokers. So this is the most important thing. We have Ophiolite Complex, peridotite, and then layered gabbro, and then sheeted dike complex, and then basaltic pillow lavas, and then deep sea sediments. Evolution of an ocean basin. We're calling back the Wilson cycle. And new ocean basins began with the formation of a continental rift. And the example, like here, splits land masses, continents, landmass, into two or more smaller segments. So this is East Africa Rift Valley, split into one arm here, Gulf of Aden, the other arm, Red Sea, keep opening. The third one is Ghaffar lowland, which is East Africa Rift. Okay? This is the formation of continental rifting. And then that will grow, so Rift Valley, East African Rift, will grow to the linear sea. And the example of the linear sea is the Red Sea. So Red Sea is the first stage, and then the second stage is the Red Sea. It keeps opening. And then as the rift keeps growing and keeps widening and new oceanic crusts form it, that will create oceanic ridges, mid-oceanic ridges like in the Atlantic Ocean. And this is the example of the formation of the ocean basin and the widening of the rift to the linear sea and then to the mid-oceanic ridges system or ocean basin. Atlantic Ocean is the example. So, continental rift. If the rifting is interrupted, you said if the rifting was successful, like what happened in Red Sea and then the Atlantic Ocean. But if the rifting didn't happen, interrupted, so failed, a failed rift valley extends from Lake Superior into Kansas. This is example here. Formerly active rift valley is failed with basalt and clastic sedimentary rocks. Why rifts fail or succeeded is not fully understood. So here we have two colors here, sedimentary rocks with this color and volcanic rocks with that color. So we have this zone, which is the rift zone, the failed rift zone, filled with volcanic rocks and then sedimentary rocks above them. So this is example of failed rift in within the continents, mid-continent rift. Destruction of the lithosphere. So now we're done with the opening, the divergent boundaries. Now we're going to the convergent boundaries. Why oceanic lithosphere subducts? We have two reasons: spontaneous subduction and forced subduction. And also, after the subduction, what happened? The demise of oceanic, of an ocean basin. So let's look at the spontaneous subduction and forced subduction. If we have cold, cold oceanic lithosphere, this will be heavy and will subduct on its own weight in 90 degrees. 90 degrees. But if it's young lithosphere and enforce it under the compressional force to subduct under continental margin or continental plate, will subduct at steep angle, at a low angle. This is at 90 degrees, old, cold, but this is young, warm, young oceanic lithosphere will subduct under low angle. So these two, this is spontaneous and this is enforced. Spontaneous subduction and enforced subduction. This is the two differences. The spontaneous always with old, cold, dense lithosphere, and young, warm, buoyant lithosphere subducted at low angles, but here at steep angles, the spontaneous. Okay, when subduction starts, the ocean basins will disappear. Here we have a parallel plate, this bluish color, and we have subduction zone here, and the rate of the convergent, rate of the subduction is so high, and here we have divergent boundaries here, but the rate of subduction is higher than the rate of the opening. What happens? This plate starts disappearing, getting smaller, smaller until it's almost disappeared. And this is the demise of these convergent plates. That was 56 million years ago, 30 million years ago, 20 million years ago, and here just today. That's what's left. Take home message. The ocean floor measured in different ways: weighted lines, echo sounds, and satellite radar altimeters. Three types of seafloor sediments: lithogenous, biogenous, and hydrogenous. And the seafloor sediments are controlled by climate. And there are three major units of the ocean: basins, continental margin, the ocean basin floor, and the mid-oceanic ridges. And then we looked at the coral reefs and atolls, and the opening and closing of the oceans, which is Wilson cycle. And by this we conclude this lecture, and we'll have 3 minutes listening at the at the national anthem of Barga State.
الشواطئ والقصور فلك المراكز في الصدور يا أيها أمس شاف رابط واليوم قد آن المسير يحيى الأمير يحيى الأمير العلم نور حياتنا والدين خير هداتنا والصبر سور صفاتنا والله مولانا النصير يحيى الأمير يحيى الأمير.
Thank you very much.